Hello, I'm José Domingos. This presentation is DevOps for Large Language Models, LLMs. It's been done with my colleague Neha Sharma. Um, so I'm going to take you through our learnings and our journey working with LLM operations in LLM operations and really the how we optimize performance and cost. So what we're covering today, we are going to divide this presentation in three parts. The first part will be the LLM operations process. What that is about is actually describing the how you work with large language models, the operations processes, and really it's important if as a DevOps community, we end up working with AI companies or within AI companies or within any organization that's trying to train their large language models. It's important we understand what they're trying to do. It's important we understand their aims and their goals. So that's what I'm going to do in the first part of the presentation. In the second part, we're going to actually show you some of our results as we work with large language models and give you an idea of what it's all about. And then the third part is actually the learnings from our experience of running AI workloads on the cloud. Hope that all makes sense. So let's look at it. So let's look at first at the wider DevOps context. The wider DevOps context is that really DevOps now has evolved into really the ability to meet business goals. And what I mean by that, it's that DevOps has become more and more an activity that's fundamental to achieving the business goals of an organization. And in the particular case of LLMs and how LLMs are being used in an organization, that's even more true. And hopefully by the end of this presentation, it will make sense why I'm saying this. But what we're seeing really is that AI organizations really use a lot of computing power and have to manage their costs extremely well and have to, of course, deliver high levels of performance. So LLMs, the large language models, is really the next step from what's called sometimes machine learning operations. And in LLMs, more than ever, size matters. If you start with a 7 billion model that you've trained, if you go to a 40 billion parameter model, the computational power that you need to train that model grows exponentially. And therefore, you know, this journey into perhaps trillions of parameters for some organizations, models with trillions of parameters, is a journey that is going to be very, very, very costly if not done properly. Large language models have this property of running better the more expensive the GPUs are. So that's, of course, an important consideration. You see rapidly evolving libraries, device drivers for GPUs and code dependencies and new software. You see the problem of fine-tuning. How many language models does a business need? You may have one language model for customer support. You may have one large language model for user support. You may have one internally. You may end up with 5, maybe even 10 large language models in organizations. And these organizations can say be a telco or maybe a retailer, right? It's not just AI companies. It could be any organization. And that's really leveraging this technology. And then, of course, custom training and managing models equates to complex ML DevOps, and we'll see why and how. So really, you can look at this as a two-part problem. The first part is training the LLM, the second part is how to run it more efficiently, the inferencing part. So in training, in the first part, we look at things like how you train models, how you incorporate RLHF, the reinforced learning from human feedback, how you track model hallucinations and outdated info, and how you can work that through. In the second part, we look at techniques for optimizing cost and reducing latency in inference tuning. So, first part. This DSMR, so domain-specific model refinement. So if you look at a model, you have the ability to, of course, train it from scratch, but that carries a high complexity, high cost, high impact, right? If you train a model from scratch, you have the ability to do RLHF, i.e., has the model responds to your prompts, you give it a thumbs up or a thumbs down, you correct the model, so that data can be used to improve your model. You have then fine-tuning. Fine-tuning, we'll talk a little bit about this, but fine-tuning is a set of techniques that allow you to extend the abilities of your model. But this is primarily, and this link here describes this really well. This is primarily for how the model answers your questions, not if you're looking for what's called factual problems. If you're looking for factual problems to train your model factual problems, then you're really linking that model to a database with retrieval-assisted generation. So you have your facts in a database, and then you link your model to that, so that information is retrieved by the model. For example, if you are doing customer support with a large language model, you really want that large language model to go into the database, which has the facts about the customer, what plan the customer is on, if it's a mobile phone, what plan he's on, what problem he's had in the past. So this is kind of the retrieval assisted generation. Fine-tuning allows you to extend the capabilities of the model to do different, to maybe answer the different capabilities, but its function is not for actual facts. It's about the capabilities and the form, or how it addresses your queries. And then you have static dynamic example selection. This allows you to ask better questions of the model effectively. And manual automatic prompt tuning allows you to actually tune the prompt so that you can get better answers out of the model. The more you go up this diagram, the more expensive and complex it is to train the model. The more you go down, the cheaper it is to actually perform those in computational terms. So let's look at some key methods for fine-tuning models. There's this term low ranking adaptation, and this is one of the PEFT, parameter efficient fine-tuning. So what's low ranking adaptation? Low ranking adaptation is when you pick a model. Let's say you pick a 7 billion parameter model, and you actually add additional parameters. Now, when you do this, the reason why you're doing this, you add additional parameters so that you can train only those parameters to enhance the capabilities of the model, to give it new capabilities, but you aim to leave the rest of the model fairly untouched. And you do this for two reasons. You do this because it becomes possible to train the parts of the model without losing the other parts that have already been trained, and you do that as well to save you costs. So because you only have to train a part of the model for new capabilities. Quantized LoRa is an improvement on low ranking adaptation with just better performance. Two software libraries that are really have come recently and have made a huge contribution in this space: DeepSpeed from Microsoft, Long LoRa from Hugging Face, And you know, there are multiple multiple techniques, but primarily these two methods, LoRa and its and quantized LoRa, its improved mathematical capability, is just is where most of the work is happening in terms of fine tuning. So, but if you fine tune, you have to look out for perils. You may end, if you pick up a model and you train it with you fine tune it with new data, you may then end up having a model that's very specific to a particular problem, that's overfitting. So it can only address questions in that problem. You may have catastrophic forgetting, i.e. the model could do certain things in the past, but after fine-tuning, you find out that it can't anymore. You may have bias amplification, in which the model always answers particular questions in a particular way that's undesirable. You may have a generalization challenges. The model is very good at a certain set of questions, but if you ask a question outside of that, the model is unable to answer. You may have, of course, hyperparameter tuning complexity. It's very difficult to change hyperparameters such as tokens and so on. You may have data requirements. You know, how do you manage the data that you're using to train the model? How you keep it versioned? How you clean that data? How you improve that data? You may have domain shift sensitivity. You know, you may have a model that's really good at doing something, but if you move it to another field, it's not so good. You may, of course, have resource intensiveness. The model, you know, how much in terms of resources you're going to need. You may end up with increased hallucinations, i.e. the model replies in ways that are not factually correct and can actually be can actually lead to problems and mistakes and errors. You have model drift, in which the model kind of slowly becomes less able at a particular field. And of course, you have ethical considerations, in which the model responds in unwanted ways to prompts by users. Again, this link from this link here from Lakera AI has lots of it's a really good link to describe these in more detail. Right, so let's look at some example. Let's say in this graph you see three tests that were performed. One test was fine tuning of a 7 billion, a 13 billion. And comparing it to a GPT-4. So a 7 billion model was fine-tuned to do functional representation. This was basically looking at chat and extracting data out of that chat. What they did is they picked up a gaming chat, and they tried to extract out of the chat what was the game that was being played, what type of game was being played, just extracting metadata in function. So this is how they trained the model. So they found that they could train a 7 billion model to be actually even better than GPT, well, much better than GPT-4. A 7 billion model or a 13 billion model, very little difference. The 13 billion model without training was better than the 7 billion model, but once they were trained, they could achieve basically the same results, much better than, say, GPT-4. Another test they did was a SQL generation. The 13 billion model was already capable of doing SQL generation, you know, up to a certain level. And then they could train both models with fine-tuning to actually achieve better than GPT-4. When the field is more complex, such as a mathematics test, GSM 8K test, when the field is more complex, then the size of, say, a GPT-4 model really makes the difference. And fine-tuning, as you can see, does not make a huge difference or not enough of a difference. It's a very complex field, and therefore fine-tuning becomes less able to deliver big benefits. So this is very interesting, and there's some from Scale, another very interesting link that describes this. So we finished looking at the overall overall training and fine-tuning of models. Let's look at LLM inference. This is the ability to actually run the model, ideally with less computing power and quicker. Yeah, so effectively less computing power and quicker. So you have three steps. Yeah, the first step is you can look at more efficient inference engines, i.e., you may look at engines that are more are quicker, that work quicker, are just more efficient at running because they have better compilers behind it, or they do distributed inferencing using distributed computing power. You have model pruning. This is where you make your model smaller, and we'll look at two techniques, sparsity and quantization. And then you have to have the ability to test. So if I make a change to my model, so if I make it more efficient, does it still do what I need it to do? Does it still so that's we'll talk a bit about benchmarking for performance tracking. Okay, so more efficient inference engines. Engines based on C++, Rust, i.e., not Python, can be can have higher performance. We'll see that a bit later. You can have inference engines that are pre-optimized for kernels. You may have specific GPU, CPU architectures, and you compile those models to work with those. You may have the ability to distribute your model in multi-GPU, multi-node intelligently. Again, a set of examples here. We'll look at CTranslate 2, for example, and we'll look at some of the Triton Inference Server and VLLM examples. So this is the TensorRT from NVIDIA. So as you can see here in LLMs, an H100 compared to an Ampere 100, you see already a 4 times the performance. This is a massive leap, and this is why everyone's getting excited about H100s. But now, if you go from, if you have a better inference engine, you can see that you can go twice the performance from an H100 to again up. So another a doubling of the performance. If you look at, say, VLLM compared with Hugging Face and then the accelerated Hugging Face inferencing, then you can see almost a 2.5 improved performance on a A100 and on a A10. Double the performance on an A10. So inference engines can help you reduce cost and latency, yeah, because they'll just work better and faster. Model size optimization, i.e., this is where you kind of look to reduce the size of your model. This is where you have techniques, and the two techniques typically are pruning and quantization. So what's pruning? Pruning is where you see you can look at a neural network as effectively a computational tree. So the data goes from left to right, from input to output. And if you have in pruning, you look for nodes where the weights are near zero, and you say all these weights that are near zero, you remove them from your model. So you reduce the number of nodes effectively. With quantization, you say, you know, all these numbers that I've got here, I'm going to move them, say, from a floating point 32 to an int 8. So you make those weights just more computationally efficient, and therefore you end up with a model that is smaller and quicker to compute. Yeah. So again, neural magic link here, you can get, say, a 7 times faster output, 7 times less memory with deep sparse. Okay, so the final key step is testing. You may be comparing an LLM versus another LLM. So you may be comparing an LLM that has gone through deep sparse before and after deep sparse. Yeah, you may be comparing prompts. You may be comparing this prompt compared to that prompt. What were the results I got? You may be comparing the temperature of a model, i.e., lower temperature model means the model tends to go for facts. Higher temperature model, the model tends to be more, should I say, creative, just more, just able to generalize further. Of course, you have to have a way to compare the scores. So exact match, BERT similarity score are two different benchmarks for models. And you want to be able to do this with code unit tests. You want to say this model and that model, run a set of tests and obtain results. And this is what Arthur AI's bench does. And there are others out there, but this is an example of doing this test bench by Arthur AI. So we've effectively looked at, first of all, the training and fine-tuning. We've looked at optimizing inferencing and reducing the size and moving using more efficient engines. And we have looked at the accuracy of models and with tools like bench. So this is kind of this finishes the overview of LLM, the LLM process, and we are now going to move to the second part of the presentation. And this is where we actually go and try some of these things out. So one way to do this, for example, what you can do is you can go into Hugging Face, and then you'll find a set of models, yeah, and you can pick a model from there, a suitable model from there. Here is the link to Hugging Face. So one of the things we did was we picked a Hugging Face model, this LLaMA 2 7B chat from Hugging Face, and we kind of took it through Sparse GPT. And what that does effectively is, as I said before, that's going through the model and removing dead weight. So removing zero nodes that are zero effectively, and making the model smaller making a model smaller and more efficient. And these were some of our results. Yeah. So when then using bench, so we used bench to test the model, and you find that going from the original model to a 50% sparsity model, a model that's 50% smaller, we are obtaining scores that are similar, yeah, and model outputs that are very similar. And that kind of shows the sort of process you can have. You know, this shows how the process can work. You may end up trying a particular setting and then seeing the results, and you can compare and keep running a set of input prompts and looking at the scores and seeing if you've ended up with some with some of the problems we've talked about, if we've had catastrophic forgetting or if you had model drift or so on. So the next thing is, of course, you're deploying your model, and you may want to look at deploying your model in the most efficient compute platform, the one that offers you the best cost, or the one that offers you or even the cloud that can offer you the right platforms you need. A lot of this testing, again, is quite important. This performance testing, having the ability to run your workloads on any cloud, or having or on-prem, having the ability to the ability to test the performance with different GPUs. If you end up with, say, an A10 versus an A100 versus an H100, you need to have processes to allow you to do this and keep on doing it and keep on gathering the data you need. And of course, this is the DevOps process and the tuning in production. As an example, when we picked up the LLaMA chat from Hugging Face, the 7 billion model, and we used a different inferencing engine with C-Translate 2, i.e., we translated the model into C++. Effectively, we obtained a reduction in memory, as you can see here, of 10 times. So 10 times smaller model, and we've accelerated the inferencing by 3 times. So 2 to 3 times faster inferencing. So this is an example of where you can then try this out on a particular cloud, on a particular platform. And this is an NVIDIA T4 GPU, but your mileage will vary depending on the GPUs and the memory you have available and so on, right? So you need to have the capability to do these tests and find out what's the most efficient cloud, platform, GPU, runtime, etc., and model effectively with translating. So some of the learnings, third part of the presentation, some of the learnings from actually scaling AI on the cloud. When you really look to then deploy your models on cloud, you really need to look at these 3 intertwined goals. You're looking for lower cost, or optimizing cost. You're looking for higher resiliency because these models are becoming more and more important for your business. You're looking at optimized scaling. You want the model to scale in a way that addresses the needs of your customers and isn't using unnecessary resources. And really a lot of organizations we talk to are looking at multi-cloud to deliver on these goals. And why? Well, if you can run your model anywhere, then that gives you leverage, right? You can say, well, I don't like this platform that I've been given on cloud X. I can go to cloud Y and have a better platform, which is more efficient for me, for my model. Or you can play cost. You can say, well, this cost here, that cost there. I like that cost better than this cost. So you can move your workload. Of course, you end up with a more reliable infrastructure if you can run your model anywhere, right? So, because if there's a problem with one set of infrastructure, you move your workloads to another set. You also have better scaling because as your use case needs change, you may end up needing more GPUs at a particular point in time, which are not available in your current infrastructure. So you may want infrastructure from elsewhere to run your model. So this multi-cloud capability really is quite important, and that's where, of course, DevOps we can help, right? Because we can be the enablers of this multi-cloud capability. But multi-cloud, as everyone knows, carries added complexity, and you need appropriate tooling to do that. It's not that it doesn't come without effort. So steps to consider when running AI workloads in production. Again, your mileage may vary. Yeah. For cost control, you can look at the most appropriate clouds. Look at the ones that have the right GPUs, look at the ones that give you the right quota, look at the ones that offer the best cost. You can find the right sized GPU infrastructure by doing performance testing. You can test your model in different GPU platforms with different memory profiles You can look at the cloud scaling capabilities of a particular platform, but effectively doing that testing will allow you to run your models in the most appropriate compute and GPUs. And you can implement multi-cloud strategies, but of course, multi-cloud strategies carry perils, and you need to effectively look at the networking aspects in particular. The networking aspects of multi-cloud are usually the most complex to address. So multi-cloud is good, but you need to have the appropriate tooling, as I said before. And then implement auto scaling to support your particular use cases. The more advanced your auto scaling strategy is, the better it works with the infrastructure scaling of the cloud that you're using, or the clouds that you're using, then the better your solution will be. There are particular auto scaling techniques again out there, and you have to try it out, and you have to see what works for you. So to conclude this presentation, yeah, in the first part of the presentation, I gave you an overview of LLMOps and what it means. We've looked at training and then fine-tuning LLM models, and we saw how they kind of they put particular needs on the operations perspective of the business, yeah. And as you probably can now see clearly, they have significant impact on the cost optimization and scalability. Yeah, so you have significant cost on cost optimization and scalability of the business. Training and deploying models in production, can lead to very high cost. So you need to be careful. You may run out of quota capacity. If you run out of quota capacity, you may not be able to train your model or run your model, even worse. And you need a reliable platform. If your business becomes dependent on these AI models, you need reliable platforms that deliver service, and the models can keep working when you most need them, when your customers when the customers of an organization most need them. And therefore, it's an extension that businesses will be looking to multi-cloud for flexibility, to meet goals, to various different clouds, not just the major clouds, but specific GPU clouds that can deliver specific services for GPU workloads, accelerated workloads. Okay, dziękuję, which is where my Polish kind of stops. Thank you. You can find Niha and I on these emails and reach out for a chat, and if you have any questions or feedback on the presentation. Thank you so much.